Hello everybody, welcome back to the Henstitute. I'm going to come back to this problem. I know that we kind of already looked at it. We answered part A and part B as a sample problem, but I wanted to just kind of look at it again. A couple of little things that are important. So in this particular problem, we were trying to determine if it was an electron or a proton, and the way we determine that is if the magnetic field is coming out of the paper. So this is out of the paper, and the particle, which is sitting right here, I think I made it green last time, is moving in this particular direction. So there's the direction of its velocity. Then its motion is tangent to this circle, but the magnetic field is coming out. That means that what we need is we need a force that's toward the center, because this is going to be a particle that's going to go around a circle, so it's going to need a centripetal force. And the only way you can have a centripetal force is if you have some kind of magnetic force that's toward the center of the circle, and the motion is always going to be tangent to that circle. But with the magnetic field coming out, if we use our right-hand rule, we point our finger in the direction of the velocity. If our magnetic field is up, if I use my right hand, it's actually going to make the force be out. So the right-hand rule would make the force out of the circle. Out of circle. What that tells me then, since the force is equal to Q times V cross B, the right-hand rule would make my force be out of the circle. If I change it by making my charge here actually be, this is a negative charge, then that will reverse the direction. So what that told me is this must be an electron, because it's going the opposite direction. So if it's out and we want it to go in, then the negative charge will make it go in, or in other words, almost like a left-hand rule if you're using the negative charges. And then to figure out the particle speed, what we did is we actually used this equation down here for part B. We said, okay, the force is equal to Q V cross B, but those are going to be perpendicular, so it's VB times the sine, and in this case of 90 degrees, because they're perpendicular to each other, and that's just 1, so we don't have to even worry about it. To find the speed then, V is equal to the force times QB. Our force was given 3.2 times 10 to the negative 15 newtons. Our charge is the charge of an electron or a proton, so the nice thing is the magnitude of the charge didn't matter, or whether it was a proton or electron. We just had to indicate it was an electron to know that it needs to be moving towards the center. And then our magnetic field in this particular case was this 4.13 times 10 to the negative 3. And we calculated all of that out to find how fast this thing was going. This gave us a very fast velocity of 4842615.012. Probably to put it into correct scientific notation, since we only have 3 on everything, we'd probably write this as 4.84 times 10 to the 6 meters per second. And we got a velocity. Now, the reason why I'm doing this problem again is I want to come back and I want to look at part C. What is the radius of the circle? So in this particular case, for part C, this is going to give us an equation as well. What we really want to do is we want to be able to set our force, our magnetic force, equal to a centripetal force, because it's going around in a circle. So the fact that it has this circular motion up here, that's going to give us the fact that these two would equal each other. Give me a second. I'm going to erase all this stuff over here. Give me a little bit more room to write. This pen doesn't erase nearly as well as the one on my board at school. Can't seem to change the size of it. And so when I do that, our magnetic force equation we already have up here. It's Q V B times the sine of theta. Now in this particular case, this sine of theta is still going to be 1 because they're going to be perpendicular to each other. And then over here, for centripetal force, this is an old equation. This is a chapter 5 equation. It's going to be the mass of the object times its speed squared divided by the radius. I didn't expect you to remember that particular one, but one that we've had before. So one of the things you notice is one of the velocities over here is going to cancel out one of these velocities. And if I were to rearrange this to solve for the radius of the circle, I would bring my r up and bring that qb down. And what I end up with is r equals m times v. So in other words, I'm basically taking this and I'm going to switch it with the b and q on the other side. And so q and b would end up on the bottom. Ta-da, brand new equation. Slap that on the equation wall and we'll be good to go. Don't have an equation wall right now, so it's just going to be a virtual equation wall. But now we have the ability to actually find this radius. This is why we needed to know what particle it was. It is actually an electron, so the mass is going to be the 9.11 times 10 to the negative 31st, rather than the mass of a proton. The speed we've just found out was this 4.84 times 10 to the 6. On the bottom, we just use the same numbers. We got the 1.6 times 10 to the negative 19 for the charge, and then the magnetic field of 4.13 times 10 to the negative 3. So in this case, we don't actually need the force because we set the forces equal to each other, and so the forces don't pop in. We also don't need that sign because when you're dealing with something going around in a circle, you always have the velocity and the magnetic field are perpendicular to each other because we're actually going to have a force that's going to be toward the center, and we've got to have a magnetic field that's perpendicular to our velocity to usually allow that. And that allows us to find that radius. Let me pause and I'll find this out. What we get is a very small radius, 0.00667618838, blah, blah, blah. To write this out, I probably just want 3 significant figures, so 0.00667. This is going to be in our normal meters, so that's the way we would write it. We could also write this in scientific notation, so it's 6.67 times 10 to the minus 3 meters, and we've got it. So what this shows us is if we have a charged particle that is moving in a magnetic field, it'll probably eventually end up in some kind of circular type of motion, since we know that force is going to be perpendicular to both the velocity and the magnetic field. Whenever we have a force that's perpendicular to your velocity, it typically causes circular motion. So that's what we have for today. I hope you enjoyed this issue or this edition of the Henstitute.